Hi everyone, today we're going to talk about Brownian motion. I'm going to do this according to my own notes, which are copied from the professor. Um, Brownian motion is a process with two variables, mu, so this is mean mu and variance sigma. And this is a sort of random process that has three conditions. So also I should say that this is a random variable xt that is evolving over time, so t is continuous. Um, so it has three conditions. Number one, let's take some random points in t1, t2, all the way to tn that are increasing. Then x of t, and again, this is a random variable, tn minus x tn minus 1, and then dot 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 to x t2 minus x t1. These are all independent. So what does that mean? It means that xt, xt as it's how it's changed between t1 and t2 has no effect on any of the other intervals, and this goes true. This is true for any interval. So basically what it means to say is that the process is random, and it any change that happens now, so it's going to be random now and it's going to be random later. It's always going to be random for any time interval you pick. Condition 2 says that x of t plus s minus x of s is a normal distribution with mean mu t, and then standard deviation sigma squared t. So this is like a very predictable, basically the difference between xt plus s minus xs as random variables. This is normally distributed with, so what does mu t mean in your mind? It might, basically, according to this mu, the Brownian motion is going to increase, on average by this value mu t, and its variance is also going to increase by this factor mu squared t. So what does that mean? That I think it's interesting to note that as time goes on, obviously the probability the Brownian motion gets farther away from where it started increases. That's what it means. Both on average terms and the variance will increase. Okay. Finally, condition 3 is that xt is continuous. So there shouldn't be, there shouldn't be any jumps. So I shouldn't be at t and then t. Suddenly I go to the next t and it should be, it's infinitely, continuous is always like infinite. It could like increase dramatically suddenly, but it's still, you still have to be able to see that it's continuous. So what does a Brownian motion look like? Here, Brownian motion starts at, let's just say x here. So x is going to be x of 0, which is, according to this formula here, this should be a normal distribution with, if we put in t 0, 0 in here, we should end up with 0, 0. So basically it always starts in the same place, and then it's going to move randomly up and down continuously. So I'm not lifting my hand up off the and then it's a random variable, so I can pick another possible thing that might have happened to it. Okay. And I guess in these examples I drew pretending that mu is 0, but it can be increasing. Okay. So then there is such thing as a standard Brownian motion, and a standard Brownian motion, shown in the slides as WT, is a Brownian motion where mu is 0 and sigma is 1. So it's like a standard normal distribution. It just, the mu means it's not increasing, and the standard deviation being 1 is fine. So then, just wanted to say that if we take any Brownian motion xt with mu and sigma again, then according to condition 2, we can write x t as normal distribution mu t sigma squared t, plus x of 0, which is yeah, plus x of 0, right? Because I've moved the xs to the other side. So there, I'm going to write it like this. And then if we take the expectation of xt, then we end up with x0, which I'm just going to say x0 is little x. So x plus, and then the expectation of this is mu t. And then the plus the expectation of no, that's it, sorry. And then the variance of xt is I think the individual term goes out, and we just end up with something like sigma squared t, I think, something like that. Yeah, anyway. Okay, finally, we're going to do, I mean, there's some talk about a filtration fn, but I didn't see any point in talking about that. So finally, we're going to talk about a calculation we can do with Brownian motion. Oh yeah, I guess there was a shorthand described here, which is that if you see this, so again, filtration is all the information available up to time. I'm gonna use t here because we're using t. So shorthand for this is if we say the expectation of x, let's say xt plus s, given ft, then I guess we're going to see the shorthand. So e of t here instead, xt plus s. Okay, so then I'm immediately going to use the shorthand here to try to calculate this this thing here, xt plus s multiplied by xs. Okay, so how are we going to, this is just a random calculation which helps us understand a little bit more about Brownian motion. Again, it's given with given time given at time 0, right? So we have no information. The filtration is 0. Okay, so the way the professor went about solving this is doing a little trick here where he does this, we subtract xs, and then we add it back again, and then we multiply it by xs here. Let me check that I'm still recording. Yes, okay. And then we're going to, by the linearity of expectation, we're going to get xt plus s minus xs multiplied by xs, and we're going to take this xs out, so we end up with e of xs squared in here. Okay, so then the just wanted to say here that this, we can find this value from, there's a nice formula for variance of xs, which is equal to, if you remember, it's equal to the expectation of x squared of s minus the expectation of xs squared. So now we know this, sorry, I forgot to mention xs is a standard Brownian motion with mu equals 0. I should have used w, too late now, and with sigma equals 1. Okay, so then this thing right here, the expectation of xs, is equal to 0 because it's a standard Brownian motion, so this is 0. And then this variance, we've already calculated it. It is just s because it's sigma squared s, but this is 1, therefore we just end up with s. Therefore, this term here is just equal to s. So from now on, we're going to replace this by s. Okay, and now keeping going with this part of the equation, we're going to take. So again, there's this nice thing here. So the expectation of the expectation of a random variable x is equal to the expectation of the expectation of x given a random variable y. So this is I forgot what the name of this is, but basically we're taking the expectation with respect to y, and then on the outside we're taking it for all y, so we can do this. So we're inside of this, we're going to change this to expectation of given filtration s. So I forgot the 0 here, with respect to this random variable. So this xt plus s minus xs, xs bracket plus s. Okay, so now the xs with respect to the if we have all information available at the time s, the value of xs of expectation of xs is just xs. So we can remove it from here, and we just have this instead: expectation of s xt plus s minus xs square bracket plus s. Okay, now this since the Brownian motion, since it's a standard Brownian motion, again this difference is going to be 0. Therefore we end up with xs times 0 plus s, and therefore we end up with s. So the final answer to all of this is this multiplication is equal to s. Now you might be curious, like I was, and ask, what if instead we try to do the same trick with t plus s? In that case, when we do this conditioning on s, instead we would do it on t plus s, and then we would end up with xt plus s minus xs given t plus s, and this would be basically what I'm trying to say is, and then this value, instead of getting s, we would end up with s plus t. So somehow we would have to end up with a minus the minus t over here. So if we try to do that same trick. So that's it. Thank you very much. See you next time.